All right. Thanks for being here on time. I feel very grateful that I don't have to deal with people constantly coming in late. That's very distracting. Oh, let's see. I was just telling him how much I appreciate everybody being here on time. I mean, you're technically, I guess, on time. It's still 1 o'clock. Usually I wait till 1:01 so I can know as a clear conscience that, I don't know. When I was teaching at another university, it got to the point to where I had to lock the door so that students couldn't come in late. So they knew that if they wanted to come to class, they had to be there on time. Otherwise, there was literally no way for them to get in. I don't think it's going to come to that in here. Homework number 1 is due on Wednesday. Has anybody looked at that already, gotten started? Few people? Okay. Hopefully that number increases. We're going to go over a couple more concepts today that lead into the homework assignment. So that's due before class on Wednesday. So 1 p.m. It needs to be submitted as a PDF file, like a single continuous file, not multiple JPEGs, not multiple PDFs, just a single PDF. And you can accomplish that with Cam Scanner or Adobe Scan. Both of those have apps for both Android and iPhones. So, quiz. If we were going to have a quiz today, which we're not, the question would be, what causes rain? So think, could you give me a good short answer on what causes rain? I explained it probably 3 times on Wednesday, but so there's a difference between being not wrong and being right. And what I hope is that when you write answers to questions like this, that you go beyond being not wrong. So here's an example of a statement that is not wrong. Rain is caused when evaporated moisture condenses onto dust particles and falls from the sky. I mean, none of those things are untrue, but there's more to it than that, right? You remember that we talked about the process for probably 15 or 20 minutes. And so I'd give that maybe 4 points out of 10 if it was a 10-point quiz and I was grading that answer. And a 10 out of 10 answer is this. And I mean, it's longer, but I don't think anything that I've written here is beyond the scope of what you're capable of. So this is what I think you should be able to say. So let me pause for a moment while you read that. So what makes this a 10 out of 10? Well, it mentions the idea of, from the beginning, not just, that there is this moisture up in the atmosphere, but like what got the moisture into the upper atmosphere. So it starts off with the warm, moist air at ground level that's rising. It mentions the 3 different causes of lifting: convergence, orography, convection. It talks about why the air is cooling, because of decreases in pressure and expanding. It touches on the idea of the solubility of moisture in air going down with cooling. It talks about droplet formation. So this class is more than plugging numbers into equations. I teach some classes where that's kind of the long and short of it, is plugging numbers into equations. This isn't that. This is a class where you have to understand the concepts to be able to apply the science. You have to be able to describe what's happening. And so I have a list of terminology that I'm going to hand out here. And these are concepts that you may see on quizzes and exams, and so you should be prepared to define everything on this list. Maybe it doesn't have to be as lengthy as that, but you should be prepared to discuss everything on the list. This is also posted on Blackboard. So if you ever lose the paper copy, it's available as a PDF. By the way, any questions about rain before we move on? Oh, I think there'll be a couple in the back. All right. So we skipped over this slide pretty quickly. By the way, I owe you 1 minute, right? Did I keep you 1 minute late on Wednesday? I thought I did.
Not us.
No? Must have been hydraulics then. I kept somebody late on Wednesday by 1 minute. If you have the 5-minute storm depth and the 15-minute storm depth, this equation allows you to interpolate and determine the 10-minute depth. And likewise, if you know the 15 and the 60, then you can find the 30-minute depth. And then you can interpolate between the 2 and the 100-year depths with these empirical formulas that are provided. And so that's one of the things on the homework assignment, is to apply both of these after looking up rainfall depths from a map. A hyetograph is a term that was defined last time in class. Here's an illustration of actual storm data. So the hyetograph is a plot of either intensity versus time or depth versus time. And if you have a tipping bucket rain gauge, something that monitors the rainfall intensity continuously, then you can know when the rainfall occurred. And so these graphs are actual data on a minute-by-minute basis when the intensity was high, when the intensity was low. But sometimes we don't have that data. Sometimes we don't have an actual rainfall hydrograph or hyetograph. And we have to extrapolate based on typical patterns for the geography in our area. So a synthetic storm hyetograph allows us to, for the region of the country that we live in, say, if you know the storm depth for a 24-hour period, like maybe you have one of those storm gauges that's just like a graduated cylinder that you go and you look every day at noon, you see how much water depth is in the graduated cylinder. And so you know between noon today and noon tomorrow how much rainfall occurred. But that doesn't tell you what the intensity was. This kind of a figure tells us that, for example, here in West Virginia, we're in Zone 2. So Zone 2 storms are typical of a really quick intensity, where over a 24-hour period, they've studied hundreds and thousands of storms, and what they've noticed is that the most intense period of a storm occurs and accounts for about 80% of the precipitation, 70 to 80% of the precipitation, in about an hour during a 24-hour period. Now, it doesn't mean that it always rains every day at 9 p.m. or something. It's not like this is saying that a storm inevitably will always start off with just a tiny little drizzle for 10 hours, but this is the average over many different storm events. And so this is what we can do, is apply something like this when we don't have any actual stormfall data to synthesize a hyetograph. It's called an SCS rainfall distribution. And you can see that different parts of the countries are under the influence of different storm patterns. And so tropical storms that come for the Gulf Coast and parts of Florida are type 3 storms, which are pretty similar to type 2 storms, but distinct. You can see where the type 3 storm, which is dashed, diverges. Type 1A storms are the Pacific Northwest, those coastal storms that are pretty gradual in nature. You know, it's this period of high intensity is a much smaller fraction of the rainfall depth than it is for the afternoon thunderstorm that predominates in Zone 2 regions. So we'll use these when we don't have actual stormfall data on a minute-by-minute or hour-by-hour basis. If we just know the 24-hour precipitation depth, then we can use this to synthesize a temporal distribution. And here is the table that figure is generated from. The table has both 24-hour storm data and the data for a 6-hour storm. And so what you would do is you would multiply the depth that you know the precipitation was. Like if you had that graduated cylinder and you measured that it was 2 inches of rainfall that occurred during a 24-hour period, then you'd multiply that 2-inch depth, if it was from this region, by the type 2 column. And then at the end of the 24-hour period, you can see where it's 1.00. So that would be 2 inches of cumulative rainfall depth after 24 hours. But it's less than 1 all the periods before that. So it's going to tell you the cumulative rainfall amount that has occurred up until that point. So you do have a problem where I'm asking you to find out the hour-by-hour stormfall depth, and I think I ask you to create a figure in Excel, like a graph of both the 24-hour and the 6-hour storm. So you'll use these details. If you don't have the book yet, you can go to the notes, and you'll have to type in the data, both the hours and the fraction, and multiply the fraction by the known depth to find out the actual precipitation amount up to a certain period. Let's look at some interesting precipitation data that's available online. Oregon State operates a website called Prism, which looks at 30 years of precipitation data and comes up with some pretty interesting maps that just show the amount of rain throughout the country. So if I zoom in a little bit more so we can see this, you can see the colors correspond to increasing rainfall depths. And so the more cool the color is, like purple and blue and green, is high rainfall depths. So if we look at West Virginia, why do you suppose that there is this section that has 50 to, some places are even in this dark blue range, which is 70 to 80 inches per year. What part of the state is this? That's where the mountains are. Yeah, so why would there be more precipitation in the mountainous areas compared to the tri-state area where we are? There's a certain word I'm thinking of. It starts with the letter O.
Orographic.
Yeah, good. Orographic effects. As the moist air is lifted upwards, it tends to precipitate. So, I mean, that's why it rains more in the mountains. It's not for no reason. It's because the higher altitude causes the rainfall to precipitate. The same thing is true in arid places like Colorado and Utah. Like, this is a rainfall map, but you can tell where the mountains are by looking at the rainfall patterns. So brown and orange is low altitudes, green and yellow is higher altitudes. So you can kind of get a sense, you know, looking at Idaho. Where are the mountains in Idaho? It's where the precipitation is higher. Now the same is not necessarily true in the Pacific Northwest. There are some mountains there, but it has to do more with coastal proximity. Sierra Nevada mountains. All right, so these are annual average precipitation. And what other sorts of stuff have they got? They've got this month's precipitation, so we can see in the month of January so far, how much rainfall and where has it been. It's kind of interesting when you're going through a really dry spell. Sometimes the monthly average can deviate a lot from the last 30-year annual average. You know, there are times when California is a sea of cool colors and West Virginia is really dry during the summer sometimes. But the Prism is just kind of an interesting website to like visualize the precipitation amounts. Let's look at the Precipitation Data Frequency Server. You're going to use this one a lot, including on the homework. So this website is from NOAA, the National Oceanographic and Atmospheric Administration, National Weather Service. What you do is just click on the map for the location that you're interested in. So if we're interested in West Virginia, I'll click on West Virginia, and then it's going to bring me to kind of a zoomed in map that I need to drag the target to the location that I'm interested. So you see this red crosshairs? If I'm interested in Huntington, then what I can do is I can find the part of Huntington that I want to get data for. So we can get real specific here. Zoom in a little bit more. All right, so if I want to know what's the rainfall patterns on campus, it's not going to vary much from on campus to Barbersville, but you can see now we've specified the latitude and longitude. The elevation is known. Now up here at the top, we can choose to either have it tell us precipitation depth data, or it can be expressed in terms of precipitation intensity. So depth would be, for example, in a 24-hour period, how many inches of rainfall was there during the period in question. Intensity would be, what's the rate of rainfall during a certain duration. So we'll look at it first in terms of depth. And we'll do English units. You could switch it over to SI units. We'll talk more about the time series data. Partial duration is more accurate than just choosing only the biggest storm in each year, the annual maximum. So the default of partial duration is for good reason that that's the default. So we clicked on a location in the map, and now down here below is a table of data. So it says in inches, how much precipitation is there? Let me zoom in a little bit. Average recurrence interval in years. So every 2 years, there is a storm that's so big that in 5 minutes, you'll get 0.422 inches of rain. That's a depth. Now, this range that's in parentheses is representing the 90% confidence interval. So this is a statistical extrapolation based on the fact that there's not a lot of weather data out there. So they're having to guess, so to speak, but they can know how good their guess is. And so their guess is so good that you've got a 90% chance that the actual 2-year, 5-minute storm is between 0.388 inches and 0.462 inches. So we'll just use this midpoint for now as kind of, we can think of as there's a pretty good chance that in a 5-minute period, the biggest storm event that would occur every 2 years is 0.422 inches. If you go up to a 100-year storm, so one that only would happen on a 1% probability in a given year, 0.761 inches in 5 minutes. So you'll notice that the amounts are increasing as you go back down through here. So 5-minute duration, 30-minute durations, 24-hour duration. So a 24-hour storm, meaning in 1 day, if the storm is going to come around once every 10 years, would be 3.65 inches. For 25 years, it's a little bit bigger, but not a lot bigger. The increases are kind of only getting larger on a marginal basis. They are larger between a 10-year and a 25-year and a 25 and 50, but the increases are kind of tapering off. Now this, remember, was the depth. If we switch it over to intensity, the figure will look a little bit different. At the top, I can have it tell me the precipitation intensity. And now it tells me that the units are inches per hour. And so the intensities are decreasing as you go down through the list. So a 5-minute storm is going to have a higher intensity than a long duration. So you've probably noticed that, like, when it rains, there may be a period of really high intensity, but it doesn't last for very long. And that's because really heavy rainfall intensity is because there's a really tall, thick cloud column, and it's not going to exist for very long. Like, once it starts raining, then that precipitation is becoming exhausted, like the moisture is coming from the sky down below, and it's going to be that the column, like the cloud thickness isn't going to be that thick over a single location for very long. So you can have high intensity and short duration, or lower intensity for longer duration. But the total rainfall amount, if you multiply the intensity by the duration of the storm, the total amount of a 24-hour storm is still going to be larger than the amount of water in a 5-minute storm, because the intensity of 5.06 inches per hour, but that's only lasting for 1/60. 5 minutes would be a 1/12 of an hour, right? So if you divided this by 12, then that would tell you the total depth. And the depth would be less than 0.11 multiplied by 24 hours. So you'll get a feeling for that, but one of the things on the homework assignment is to refer to this table, and so you could download it as a CSV file from here, or you could just select the data and paste it into Excel if you're going to make a graph. It has graphs, like we can look at the IDF curve, and we looked at IDF curves in class on Wednesday. So this is showing the different return periods, intensity, and duration. So IDF, intensity, duration, frequency. So a couple of different ways to visualize the rainfall data. Any questions about this data? It's based on a data set that's called NOAA Atlas 14. So it's a way of finding out what's the precipitation. Like this is called a, what do they refer to this? A probabilistic rainfall distribution. Probabilistic meaning that it wasn't like you're predicting how much runoff there may be from a watershed just based on statistically derived rainfall data. And so anytime you're saying, I want to figure out how much water will come out of the watershed every 10 years during a 10-year storm, then you use as an input for that the probabilistic rainfall data that comes from NOAA Atlas 14. So that's another interesting data set. And then we can look at individual rain gauges by going to the Climate Data Online data set. And this is another one that you're going to use on the homework assignment. So when you do, here's where you should click. Down here where it says Data Tools. If you click on Data Tools, then find a station. You could type in a search term, like if I was interested in Minneapolis. I don't know how to spell Minneapolis. I better choose a different city. Let's do Denver. I know how to spell Denver. All right, Denver. And data set. I want to look at the daily summary of rainfall data. And I want to have precipitation data. Now, it's showing me these are all the rain gauges in and around Denver. And if it's really big, that says 8. If you zoom in on it, it's because there's several different rain gauges in a clustered area. I'm mainly interested in airports because the best weather data is near airports. Looks like we don't have one right at the airport in Denver. But when you click on a location, it'll tell you down here what the period of record is, like what range the data starts and ends at. And so you can hopefully find a place that has a good period of record. So far, I haven't found anything that goes way, way back. Let's take a look at Huntington, for example. Huntington, West Virginia. Because the Tri-State Airport has a pretty good data set. Precipitation. I'm surprised it's not showing up, honestly. It might have a different data set. Maybe they've got hourly data there. I'm really striking out. Columbus. All right. I have a good feeling about this. Okay, Columbus Airport, 1945 to 2014, and it's got 97% coverage during that period. So usually if you find the airport of a big city, they will have had a weather station there for a good long period of time. And the way that this works is that you have to like order the data, so to speak. So I'm adding it to the cart, and then I'll give them my email address once I check out, and they'll just send you an email when the data is ready. You don't want a PDF of the data. You want to have the actual data in an Excel file, so comma delimited CSV. And then you can choose the range of data. That stuff in Columbus went back to 1945, so let me just say that I want it from December 1st, 1946 to the present. All right, continue, then you tell them what you want to be included, so the station name and precipitation. I don't need to have the description of cloud cover, the sunshine intensity or wind or anything. I just only want precipitation, which includes snow depth if it was snow. And then you give them your email address, and they'll send you an email when the data is ready to download. Or you can just click check order status and it'll tell you when it's ready. So it's in the queue right now. Still in the queue. Depending, I guess, on how busy they are, I've seen it take as long as 2 or 3 hours to get the data. So you don't want to be trying to work on this immediately before classes due, because it could take a little while for them to have the data available for you to download. And once you do, then what you'll find is, let me just show you what it looks like. I think I've got a data set from last semester. Or last time I taught the class anyway. I must not have it handy. Well, oh, it's ready to download. So what it is going to pull up is the precipitation depth will be in inches to the nearest hundredth of an inch. So here it is. It's showing every day since 1948. I mean, it had 90%, 97% coverage, and so there will be a handful of days that are missing from the record. But it tells you the precipitation depth in hundredths of an inch. Although this may have been converted over to inches already now that I look at the units of it. Like if we sort this from largest to smallest, yeah, I think that that's already been converted to inches, because, you know, from 1946 until now, what this is saying is that the largest amount, the largest precipitation amount in a single day that they've observed is 5.31. And that wouldn't make sense if that was 5/100ths of an inch. But that does make pretty good sense if that's 5 inches during that period from 1946 till now. So what I've done is I've just sorted it from largest to smallest. So you can see that out of, how many years is that from 46 until now? 54 plus 23. That's like more than 70 years worth of data. The largest precipitation amount that we've seen in more than 70 years is 5 inches. So you can kind of get an idea of historically how big storms are at a certain spot. Like if we've got this daily data that goes back that far, then you could say, well, now I'm trying to plan for a project in Columbus, and I want it to be, this project, I want it to be sized appropriately so that it can handle the 25-year storm. So you could use Precipitation Data Frequency Server to find out what is the 25-year storm at your project location. And also you could check on the actual storm data at, in that city to see, like, it's always good to analyze things from a couple of different perspectives and double check the data that you're using. And don't just rely on things, but verify it. So it's interesting to look at the actual station data. Sometimes during really large storm events, like there may be a precipitation gauge out by the Greenbrier, and it would be interesting to see what that gauge was saying for the storms that happened in 2016 when they had a lot of flooding out there. Maybe we'll do that later in the semester. All right, so we were national data set. We've looked at that. If you're going to create your own intensity, duration, frequency curve, you can do that in a procedure that's similar to what I just demonstrated in Excel. Like, if you know the total number of days that are here, so let's just say this this data set here, if we count how many entries there are, so equal count all of these, so I'm doing shift, control, and the down arrow, and it'll take me to the bottom of the list. So looks like there's around 22,000. I don't know why it didn't count. Maybe because it's not a number. Let's do this one. All right. 22,000 entries, so that's days. If I wanted to know how many years of data, then I'd divide this by 365.25. And then that would tell me how many years of data I've got. So 62 years of data, based on the fact that there was not complete coverage. Looks like we've got 62 years of data. So the 63-year storm is 5.13 inches. What this slide is saying is once you rank order data, then you can calculate the return period using the Weibull formula, where the return period is the number of years of data plus 1 divided by the rank in that data set. So by rank, what I mean is, like this is, I'm going to delete the snow and snow depth. This is the first largest in our data set. This is the second largest in our data set. So let's say we've got 63 years of data. What this formula is saying is T, the return period for this one, T, if N, the number of years of data, is 63. So let's let N be 63 years. Then T is N plus 1 divided by M. So N plus 1, N plus 1 divided by 1, because this is our first ranked. This is the return period of that particular storm. So 1, 2, 3, 4, 5, and so on. So we could drag this down, and I think I must not have divided by that. Need to divide by third time's the charm. All right, so 5.13 inches corresponds to the 64-year storm in Columbus. 4.8 inches corresponds to the 32-year storm. And obviously, it's not common to talk about the size of the 64-year storm. And so you may need to interpolate, just as an illustration of how you do that. This is like a similar approach. Like if we went and got this rainfall data and we had certain rank, then we could calculate the return period associated with it. We've done that so far. But the linear interpolation between time periods is, let's say you've got your data, which is a 33-year storm and a 16.5-year storm. So the difference between those is 16.5. And the difference in rainfall depth between them is 1.3 millimeters. And so the slope is how many millimeters per year is going down as you reduce from the 33-year storm to the 16.5-year storm. So the 25-year storm is going to be between the two. So this is just a really precise way of finding the difference between the 16.5-year storm and the 33-year storm. And so we could do a similar thing to this data, we could say, we know what is the 64-year storm rainfall depth and the 32, but I want to know the 50-year storm rainfall depth. So we'd need to linearly interpolate between the two. So it's going to be in the ballpark of around 5 inches is the 50-year storm, according to this observed data at a single point. A few years ago, I set out rain gauges, one in Huntington and one in Ona, and I compared the difference because it's about 10 miles between the two rain gauges, and I was just interested to know how much the rainfall would differ. And you can see that over the course of about 3 months, the rainfall depths differed by about 15%, even though they were only 10 miles apart. So this is just an illustration of a term that I used previously, spatial variation. We talked about temporal variation and spatial variation. Spatial variation is just that even when you're relatively close together, there can be differences in precipitation depth. If you set out a rain gauge, you have to be careful because they're very sensitive instruments and they can be thrown off by a variety of things, such as if the rainfall gauge is too close to the ground, drops of water that fall outside of the rain gauge can bounce from the ground up into the rain gauge. Especially in the middle part of the storm, when the soil is already saturated, there can be splashing from the area around the rain gauge that shouldn't be getting into the rain gauge, but it can. So usually rain gauges are elevated up off the ground enough so that there won't be any splashing. They also have to be kept clear of buildings and vegetation that would cause any obstruction. So you can see this illustration is saying that it should have a clear view of the sky of at least 45 degrees, and maybe that angle should be even less so that any sideways precipitation isn't going to be blocked. You wouldn't want the rain gauge in the shadow of a building or a tree when it's raining. Water can evaporate from a rain gauge, like especially the kind that you're only going to be monitoring once every 24 hours. The daily depth rain gauges, if it rained in the morning and then was hot and dry all afternoon, there could be a significant amount of evaporation that occurs during that period. And so automated rain gauges that will trigger, they call them tipping bucket, when automatically when 1/100th of an inch of water accumulates inside of the gauge, it will trigger a tip and it will record a timestamp associated with that. And you're less likely to have any problem with evaporation when you use a tipping bucket rain gauge like the kind that they've got set up out on the Buskirk field. But those instruments do have to be calibrated. They can get dust or leaf litter can get into those rain gauges and can clog up either the funnel that goes into the tipping bucket, or even a layer of dust inside the tipping bucket could displace some of the volume, and then it would be tipping too frequently and reporting an unrealistically high rainfall intensity. And people could write down the wrong number or not be looking at the meniscus from horizontal perspective, and so there's observer errors that can pop up when it's a rainfall depth gauge. Occult precipitation. The word occult sometimes is used to describe like satanic stuff, so it's kind of, I don't know, a strange use of the word occult for precipitation, but what it means is it's fog that that wouldn't be measured on a rain gauge, but dew and fog can provide moisture to the ground and to vegetation that a rain gauge maybe wouldn't account for. So sometimes the precipitation quantity that's reported on the weather or at the airport wouldn't include the contribution of dew and fog. Same thing with low intensity precipitation. Sometimes the gauges have a poor sensitivity to those. There are some interesting different techniques that are used to extrapolate measured precipitation data over a watershed area. So if you were measuring the precipitation depth at several different gauge locations, and this polygon represents our watershed boundary, that we're interested in a certain area. The least accurate way to find out how much rainfall fell in your watershed would just be to take a simple average. So if you're going to only include the amounts that are either in or near your watershed area, so here they're including in the average these ones that are outside if it's within some threshold distance. You know, like if it's within, maybe if this was on the order of a couple mile watershed, if it's within 1 mile of the boundary, it looks like they're including it in just a simple average. And so this is suggesting that you'd have 3.26 inches in the case of just using an aerial average. The Thiessen method does better than that, because here the rain gauge that's inside the watershed is weighted equally with one that's outside the watershed. And I think there's a pretty good argument to be made that it shouldn't be weighted as heavily if it's outside the watershed but near, compared to one that's inside the watershed. And so the Thiessen method, what it does is it interpolates between rain gauges, and what you'll notice is that there are these lines that are drawn halfway between 2 points. And so you look here at Hang Tree versus Upper Falls. What they did is they drew a line between the two, and then they'll assign the hang tree depth to the entire area that's on the hang tree side of that line. And then the same thing is true between Hang Tree and Crystal City. They drew a line between the two, and on the Hang Tree side, they assigned the hang tree depth, and on the Crystal City side of the line, they assign that lower depth. And so you figure out what area of the watershed should be applied to which rain gauge, and then this is an aerial average that's assigned to the contributing area of each rain gauge. And so you'll notice in this tabulation that, for example, the Wyatt has a pretty big contributing area, 2.94 square miles, but the Lower Falls has a pretty small contributing area, just 0.82 square miles. So the Thiessen method is a way of coming up with a more accurate representation of the average. And here we had 3.26 inches, but when we use the Thiessen method, the estimate's 4.63 inches, which is more accurate. But we can do even one better than the Thiessen method by applying isohyoidal. Because the Thiessen method, what it does is it applies the same rainfall depth to all of the area inside of this polygon. But if you just go on the immediate other side of the boundary, suddenly the area is, this zone is getting 4.13 inches. And so there's like a discrete jump between two very dissimilar rainfall depths. The isohyoidal method says let's have a more gradual increase in the rainfall depth, because that's probably more in keeping with what really happened out in the world. Like what really happened is that there's going to be zones of high intensity and gradually decreasing zones of lower intensity. And so this is a more gradual application of the rainfall intensity. So you have the actual depths and then you interpolate. You can do this by hand. There are computer programs that will come up with the isohyoidal just means that everywhere along this line is assumed to have a rainfall depth of 4 inches. And then everywhere along this line is 5 inches. And so then what you do is you'd calculate the area between those two lines, and you'd assign it to the average depth, which would be 4.5 inches between it. So the programs that, that we have access to for watershed modeling can use all of these different effects to extrapolate and to come up with the most accurate rainfall depth for the watershed that we're trying to simulate. So this is from that PRISM map, and we see that there's a huge distribution in the rainfall quantities across the U.S. Certain parts of the West are very arid. Unfortunately, the largest growth in the United States happens to be in places where they have the lowest amount of water. So populations are growing really heavily in in Arizona, New Mexico, Utah. So the southwest part of the United States has drought conditions, and that happens to be where there's the least amount of rainfall. We've talked about the orographic effect on Oahu, and both of these show that there's quite a lot of variability in precipitation depth from place to place, spatially distribution across the United States. Temporal distribution isn't just in the 24-hour period that you can have periods of high intensity and periods of low intensity, but also seasonally. And it's interesting to look at different parts of the country, how what is the rainiest months for one region may be the driest months for another. So looking, for example, at San Francisco, where in San Francisco the summer months of July are almost completely dry, very little precipitation on average in the Pacific Northwest. But then through the Midwest, the summer months is when most of the precipitation occurs. So if you look at Chicago, Kansas City, Denver, Rapid City, it has the highest precipitation during the summer months. And that ties into the different reasons for precipitation. So in the Central Plains, where convection leads to frontal convective lifting, then you're going to see the summertime months having the highest precipitation, where coastal areas are less influenced by convection, and it has more to do with the storms as they come from the ocean. And then there are certain places like Boston that are pretty constant. So you really have to change your assumptions depending on the location of your project and use location-specific rainfall data, not only just depth, but also understanding seasonal differences in precipitation. So this figure shows the average number of days with thunderstorms, and along the coasts they have very few thunderstorms in a year, like 5 or fewer. And then in Florida and parts of the coastal areas, they may have 70 or 80 days of thunderstorms in a year. Okay, so the last thing we're going to talk about today is probable maximum precipitation. And PMP is how they design dams. We no longer think about like the 50-year storm or the 100-year storm. We want to size certain pieces of infrastructure so that they are sized with storms that are so big that they'd only come around once in every 10,000 years. So probable maximum precipitation just looks at limiting values like what's the maximum amount of moisture that could be in the atmosphere, and how tall of a column of clouds could we see converging from 3 locations simultaneously. And so they've studied all across the world. This figure is showing different cities, and it's the maximum precipitation depth for storms of different sizes. And it's interesting that it follows kind of a pretty clear pattern. They do a regression analysis and found that if we have time on the horizontal axis here and rainfall depth on the vertical axis, then it follows this curve where the maximum precipitation that you're likely to see for a one day, so 24 hours, the biggest storm ever seen was in Reunion, which is an island in the Indian Ocean, and that storm depth was about 3 meters. 3 meters. So that's like 70 inches of rainfall in one day. If you wanted to figure out what's the biggest storm that you could see over a 1-month period, so 30 days, the biggest rainfall depth that's ever been observed for a period of 30 days, 10 meters. That's almost hard to imagine, 10 meters of rainfall. But anyways, that is how, like, rather than just looking at the 100-year or even 200-year storm, probable maximum precipitation in the United States, they've done studies to find out for watershed sizes of a given area, what is the for a certain duration and depth what you're likely to see for watersheds of certain sizes. So the bigger the watershed is, the lower the maximum observed rainfall is, because it's not likely that you're going to have a really big storm over the entire United States at the same time, but you could have a really big storm over a smaller watershed at once. Okay, so that's all the time we have for today. The weekend awaits you, and so does homework number 1. So as you work on that, I'll be checking my email over the weekend. If you have questions, you can feel free to send me a message or call me on Teams. And if I'm available, I'll be happy to help you out.